Okay, I thought we'd finish off this week by completing our discussion of fractals and look at fractal objects and how we can generate fractal objects. And what we'll see here is very different from what we did with the Mandelbrot set. We'll see actual geometry being generated and get a better idea of what fractional dimension actually means. Now, the way that this fits in is with some of the things we're going to be talking about over the next couple of weeks that fall under the sort of the general heading of modeling and simulation. And so if we start with the idea of what we've done so far, where we've just dealt with geometry and we've modeled objects by polygonal meshes of some sort, we've argued that there are limitations to just how much geometry one can generate. Now, of course, you can do something like texture mapping or one of the other mapping techniques to make things look a little more realistic, but still the underlying model is still limited by how much geometry you really want to render and store. We'll talk starting, I guess, next week about making our models hierarchical, where parts of the model can depend on other parts, and that will often simplify the geometry quite a bit. Curves and surfaces. We'll talk towards the end of the course about how we can do curves and surfaces, but that still all fits as some sort of a geometric kind of model. Now, an alternate approach that we saw a little bit earlier this week was particle systems, where we did a little bit diffusion and we showed how that could model something like ant behavior or prey predator kinds of things. Fractals give you another tool in your toolbox to use procedural modeling, where you have even the geometry or the particles controlled by some sort of procedures, programs that we would write as we did with agent-based modeling. So fractals just going to give us another way of approaching the general problem of how do we do modeling and then use models as part of simulation. So let me start by going back to this Sierpinski gasket, which we've seen many times. And when we presented the Mandelbrot set, we talked about that this object, it gets a little bit weird as we start subdividing over and over again, because each time we subdivide, the area that we color green gets smaller and smaller, and I think it's pretty clear that's going to zero. But on the other hand, if we add up the total perimeter that each time we subdivide, each triangle becomes 3 triangles, and the perimeter of those 3 triangles is greater than the perimeter of the original triangle. So every time you subdivide, you get more and more perimeter or edges, and as you have go towards an infinite number of subdivisions, you get a perimeter that's going to infinity, while at the same time the area is going to 0. Now that is not a standard geometric object. I can't say because it's living in the plane it's a 2-dimensional object, nor is it a curve that I could say is a 1-dimensional object that lives in a plane. So it's something else, and it's something that's puzzled mathematicians for over 100 years. So let me go back to the problem that actually started the discussion of these not normal geometric objects, and it's the problem that I think arose in England somewhere around the middle of the 1800s, where people say, well, how do you measure the length of the coastline of England? And it turns out it's not a simple problem, because it depends very much on the ruler that you have available. So we argue like this: suppose I was trying to measure the length of the coastline of England. Well, what I might do is go get me a map of England of some size and lay a string along the coastline, and then using the scale of that map and the length of that string, I could get a first answer to what the length of the coastline of England is. But then I could say, what if I got a map that had greater resolution? So I get maybe a bigger map or a bunch of littler maps, and I start noticing that there's a lot more detail along the coast, a lot more indentations and protrusions sticking out. So now I lay my string along there and I measure the length on this bigger map or set of maps, take into account the difference in scaling, and lo and behold, I get a longer length. They say, well, what I need is an even better map. And I could keep repeating this experiment to where I go and I walk along the coast and somehow measure the length that I'm walking. And if you even repeat this down to sort of an atomic level, you start getting longer and longer distances. So the answer sort of depends on what the length of the ruler that you're going to let me have to use is. And if I fix the length of the ruler, the minimum distance it can measure, I can get a measure of the length of the coastline of England that we might all agree on. But this dependency on the ruler is something that people had considered. There's also a second aspect which is crucial to this, is that as I start getting maps of higher and higher resolution, I notice that the little pieces of coastline look the same as they looked, or similar to the way they looked on the map with less resolution. I see more little indentations and protrusions, but if I didn't know the scale, I'd say I wouldn't know which map they came from. So this is the notion of self-similarity, that a part of the whole looks very similar to the whole when viewed at a lesser resolution. So those are the two pillars of fractal geometry that was created by Mandelbrot, who was at it was at IBM for a long time doing this work. So the two key features are the dependence on the scale, that's the length of the ruler, and self-similarity, that a part of the object looks like the whole of the object, and every time I subdivide it, I get something that looks very, very similar. Now, in the graphical area, people discovered this technique and said, hey, this is a really good way of modeling things like topography and mountains, and we'll see that. And when the first paper was sent out to review for on using fractals for computer graphics, Mandelbrot objected and said they're not doing it quite right, and so they wound up calling it graftals in the first paper. But everybody now calls them fractals. In fact, the mathematics is much deeper than I could possibly show in a lecture or two, and Mandelbrot's derivation, and there are many books on this, and his followers, they create geometry which is correct in the sense that as you start subdividing, you don't get things that cross over and mountains that fold into themselves. Well, we're just going to look at some very simple examples right now. So let's start with a simple one known as the Koch snowflake, and if you put it into if you close it on itself, it becomes the in linear on top, it's the Koch curve. If you sort of close it on itself, it becomes the snowflake. So the idea here is that you start with a little line segment of length 1, and you subdivide it into 4 line segments, each of length 1/3, and these two form two sides of an equilateral triangle. And then the recursion is that I take each of these sides and now subdivide it into 3 parts, and then replace the middle part by the 2 other sides of an equilateral triangle. So it gets more and more detailed as I do this. And I think it's pretty easy to see a couple of properties here. One of which is that the length here is obviously, it's 4/3, which is longer than the length of the little line segment I started with. And every time I subdivide again, I get 4/3 times the length of what I started with. So that we're getting infinite length, but also notice that if I were to put a little box around it of, let's say, height 1/3, and notice that every time I subdivide, the new curve is going to fit in that same box. So I'm getting a curve that has infinite length, but on the other hand, it doesn't extend over any kind of an infinite region. It's constrained to be in that same area. And if you take the snowflake example, where here we would start with 3 line segments for an equilateral triangle, let's say each has length 1, and now each of those is subdivided as I subdivide it up here, I start getting something that it looks gets a lot more detailed, and I subdivide each of these little line segments. So again, you have something that fits inside of a box of finite size, but keeps getting longer and longer and longer. And so it has all kinds of other odd properties. For example, as you do infinite recursions, you get this curve that's continuous but doesn't really have derivative anywhere, because it's changing at every point. So it's a very odd odd object. So how can we get a definition of what the dimension of this thing might be? And there are various ways to do that. This way I'm going to show you is actually I think, very straightforward. So let's start with this idea, that if I draw a line segment of length 1, a square with a side of length 1, and a cube which has length 1 in each dimension, we should all agree that if any definition I'm going to make of fractal dimension, this should be a one-dimensional object, the square should be a two-dimensional object, and the cube should be a three-dimensional object. So starting with that, let's argue as follows. Suppose I scale each of those objects by a factor of h. So for the line segment, I would be dividing it into n parts, each of which was scaled by this h. Here would be h would be a third, a third, a third, and I get 3 line segments out of that. If I scale by that same factor on the square, I get 9 little objects here, each that have a side length of a third. And likewise for the cube, I rule the sides into a third, and I get 27 little subcubes, each of which have length h, 1/3 on its side. So if I start counting the objects, I could say, well, here I had 3 objects, and when I summed them together, I got the whole, the 100% of what I started with. Here I subdivided by that same factor, but I got 9 objects, which summed together to give me what I started with. And here on the cube, I got 27 objects that summed to what I got. So in one dimension, this subdivision gave me 3 objects. In 2 dimensions, it gave me 9. In 3 dimensions, it gave me 27. So if I extend that idea, I can get a notion of dimension by saying how many similar sub-objects do I get? Because here I got subcubes, here I got subsquares, and here I got little line segments. How many subdivisions do I get when I apply a scale factor? So if we follow that line of reasoning and say, well, for the line you got n, for the square you got n squared, and for the cube you got n cubed, and the whole is the sum of the parts, then by scaling by that factor d, I got n to d, where d is the dimension, objects, and that gave me the whole. And if I take the log of both sides, I can solve for the dimension that says, how many objects do I get over, how many objects do I get, divide based on the scale factor. The scale factor is 1 over n, but that gives me negative of the log. And so this is a very interesting measure of how we can get a notion of dimension for these kind of objects. So let me show you those examples for the ones we've seen, the Cott curve and the Sierpinski gasket, and then I'll show you 1 or 2 others. So for the curve, we scale by a factor of 3 each time, so that gives me the bottom, log of 3, and we create 4 new objects each time we do that, and so we get a dimension of log 4 over log 3, and I think you should all know that it doesn't matter what base I take this log in. And that gives me about 1.26. So here's an object that lies in the plane that has a dimension which is greater than that of a simple curve, which would have dimension 1, but doesn't have the dimension of a surface. A simple surface would have a dimension of 2. Now for the gasket, what I did is each time I did that, I got 3 new objects because I threw away the middle, but the scale factor was 1/4, so it's not natural log 4 here. Natural log 3 over natural log 4 is about 1.6. So now I have an object, again, that's not two-dimensional, but lies in the plane and has a dimension that, if we look at it, it's higher than the dimension here, which, as we'll see in a minute, is some measure of the roughness of the thing that I create. Now, what if I do this in 3 dimensions and start creating subdivisions like we did with the cube? Well, we already saw one example, which was the 3-dimensional Sierpinski gasket. So in this case, what I do is I take these 4 subcubes, subtetrahedron from the original tetrahedron. I got that by scaling by a factor of 2, so the dimension of this object is natural log 4, I created 4 tetrahedron, divided by log of 2, 1 over the scale factor. That gives me, turns out in this case it just gives me 2, but it's not a simple two-dimensional object because it has three-dimensional points inside. It doesn't all live inside of the plane. Here's another cute one which says, take the cube and now push through each of the centers on the faces, knocking out those blocks. So if I push through the first time, I knock out 3 blocks. If I push down from the top, I push out 2 more. And if I push from the side, I'll have 2 more blocks that I push out. So I've removed 7 blocks, sub-blocks by doing that. And so I have 20 little objects here. I've scaled by a factor of 3. I divided by a third along this length. And this is an object which has a fractal dimension of 2.7 something. So this gives me a nice measure. And now the next thing you might say, well, it's nice for these nice sort of regular objects that you've shown me, but what about if I want to have something that I can use in a simulation? It's something I could use for modeling. So let's take another approach that adds a little bit of randomness to what I've been doing. And the notion here is midpoint subdivision, and we're going to talk about what's called fractal Brownian motion. So suppose I take 2 points and I draw the line segment that connects them and look for the midpoint. Okay, that's easy to do. I just take add up the two representations and divide each component by 2. Now suppose I go off in the normal direction an amount that varies randomly. And we're going to use a Gaussian random number generator here. The reason being I don't want to have lots of large displacements from the midpoint. I want to have a lot that are sort of concentrated around 0. So I can go in either direction here, and that gives me a new point, and that's the basis of my subdivision. Find the midpoint, find the normal direction, go a random distance along the normal direction, put a point there, and now keep repeating it. So I can subdivide on the left, I can subdivide on the right, compute the 2 normals, and go a little bit. And each time I'm going to scale the Gaussian random number generator because I have a shorter length here, so I don't want to take as big excursions from the midpoint. And that's easy enough to program. And if you do that, you get what I said is fractal Brownian motion, where generally the variance is given by the length, which keeps getting subdivided by 2 each time, and by the dimension that you want to have, where d is the variable that you're going to be able to adjust. If that variable is 1.5, that it's halfway between a simple one-dimensional curve and going up to 2 dimensions, that gives you what's exactly Brownian motion in the sense that physicists study Brownian motion. Brownian motion is the random movement of particles for example, in air or in a fluid. It was studied by Einstein originally, and the model that's used there is somewhat different from here. But if you pick the dimension to be 1.5, you get something that is in fact Brownian motion. But the interesting part here is that by taking values other than 1.5, you can get curves that range from being very smooth to being very rough. Well, here below you see an example of, here's the first subdivision, here's a second subdivision, a third subdivision, a fourth subdivision up here. And notice you're getting a shape that looks somewhat like looking at the top of a mountain range from a distance. And in fact, that's one of the major uses of this of fractal Brownian motion, or fractal mountains and fractal landscapes. So if you wanted to apply that to a terrain, you might do something like this, that you start with a tetrahedron. So I'm going to get a fractal mountain out of this. I start with a tetrahedron, and what I do is I start doing midpoint subdivision. So it starts looking like what we did in that very much at the beginning of the course when we did the 3-dimensional Sierpinski gasket. But now I'm not going to remove anything. But what I am going to do is I'm going to do the fractal subdivision on each of the sides. So I'm going to take this point over here, move it in the normal direction a little bit, so I get a new point over here. The gray under here is the original tetrahedron, and these lines are for the displaced vertices. So this vertex gets displaced a little bit up here. This vertex, in this case, what I've done is I've kept the 3 original vertices fixed. I could have perturbed them too, and you get something that you can see the shell out here of the same number, the same number of polygons we got, but just their vertices have been displaced. And now I start doing that, and I can render that with shading. I could render that as a mesh, but you start getting something that looks a lot more realistic. It starts actually looking like a mountain. Now, depending on what value you pick over here for D, you can get a very smooth surface. So if I pick D pretty close to 1, then what I would get is something that might, a surface that might look like a kind of a flat deserty shape. If I picked a higher value, closer to 2, I get more jagged kinds of mountains. And this is really the standard technique for generating these kinds of terrains, in whether it's in an animation, in a movie, or in a game. And notice finally that one of the nice things about this is you generate the geometry on the fly. I don't have to really store anything. I could just keep repeating the algorithm every time I need to do the geometry, as long as I can restart the random number generator at the same point, or with the same seed each time. So this is something I think you might want to use for projects. Everybody's always interested in how we use fractals, so here's at least we have an introduction to the field.